tardes, soy Dr. Simon Nicholas Kemp de la Universidad de Guadalajara. Me da mucho gusto que presenta a nuestra gran invitada hoy, muy distinguida, que hemos intentado tener presencialmente antes en la Feria Internacional del Libro, pero este año podemos invitarlo aunque sea virtualmente. En el marco de la Feria Internacional del Libro y el 7º coloquio de astronomía, universo y sociedad, presentamos la conferencia de la doctora Jocelyn Bell Burnell. Doctora Jocelyn Bell Burnell es una astrofísica más famoso por su descubrimiento de los púlsares con radiotelescopios durante su tesis doctoral en la Universidad de Cambridge en 1967, de lo que nos va a contar en su plática. Era una nueva clase de objetos astronómicos y su descubrimiento muy inesperado tenía mucha significancia. Muchos pensaron que ella debe haber ganado el Premio Nobel de Física para este descubrimiento, pero se lo otorgan a su director de tesis y el director del Instituto de Astronomía en 1974. Pero ha estado muy famoso desde entonces. Todos los libros de astronomía popular desde los 70s lo han mencionado a ella y su descubrimiento en la parte exótica al final de los cuásares, pulsares, hoyos negros, etc. La doctora ha trabajado en varias instituciones y universidades, incluyendo la Universidad de Southampton, University College Londres, Observatorio Real de Edimburgo, directora de proyectos de telescopio James Clerk Maxwell, la Universidad Abierta, que era como la primera universidad de aprendizaje remoto, ¿no? Cosa que nos ha tocado a todos de nosotros los últimos 18 meses. Esta universidad fue pionera en esto. Dean como rectora de la Universidad de Bath. Ahora es profesora visitante a la Universidad de Oxford. Ha sido presidente de la Sociedad Astronómica Real y el Instituto de Física. En 2018 ganó el premio Breakthrough en Física Fundamental para su descubrimiento de pulsares. Con el dinero del premio fundó un sistema de becas y fondos para mujeres, minorías y refugios para ayudarles a estudiar física y ser investigadores. En 2021, este año, ha ganado la medalla de oro de la Sociedad Astronómica Real, la medalla Copley de la Sociedad Real, solamente la segunda mujer para ganarla, también una medalla de una revista alemana. Todo eso desde julio de este año, entonces ha tenido una temporada muy productiva en los últimos meses. También es dama del Imperio Británico. Hoy invitamos a la doctora Jocelyn Bell Burnell a dar una plática sobre el descubrimiento de pulsares, o como va a estar en inglés, the discovery of pulsars. So, Professor Bell Burnell, when you're ready, please start your talk.
And thank you for the opportunity to be with you today. I'm sorry I cannot be there in person, but at least with Zoom we can do some things. I'm going to tell you a little bit about radio astronomy and a bit about quasars by way of introduction. Then I'll talk about the discovery of pulsars and say a little bit about what pulsars are. So this is a whole electromagnetic spectrum. Here is the bit that we can see with our eyes. And from the red end of that, we move into infrared, then millimeter, then radio. So I'm talking of work around about this part of the spectrum. Radio astronomy started at the end of the Second World War, about 1945, when some radar experts took some radar equipment back to their universities. They were particularly interested in the radar receiving equipment. They were not interested in the radar transmitting equipment because they wanted to see if there were things in the sky that gave out radio waves. They already knew that sometimes the sun gave out radio waves. It had jammed their radars during the war. So it's developed by people who have worked in radar, and they point their primitive radio telescopes at the sky, and they find lots of things up in the sky are emitting radio waves. When they ask their optical colleagues what there is at certain positions in the sky where they're getting radio waves, the optical astronomers say, well, it looks a bit like a star, but it's not any kind of star that we have known before. So they became known as quasi-stellar radio sources, or quasars. The optical astronomers also were able to say that those objects that sending out the radio waves were very, very far away. So they're strong and they're very far away. Usually distant things are faint, and it's the nearby ones that are strong or bright. These things became known as quasars, quasi-stellar radio sources. Now, to tell you how I got involved in this story, this is a map of the British Isles, and it shows where I started life, where I had my schooling, and where I did my bachelor's degree in Scotland. That's 1, 2, and 3. And you can see that those 3 places are all in the northern part of the country and in the mountainous part of the country, whereas Cambridge is down here in the affluent south, close to London. I'm sure you don't have such things in your country, but in our country, I suspect there is a gradient. People from this part of the country are deemed to be uncouth savages, whereas down here is the ultimate in civilization, the perfect place. Well, when I got to Cambridge, I discovered that everybody there seemed to be very clever. And I didn't think I was as clever as they were. I thought perhaps they'd made a mistake admitting me, that they would discover their mistake and they would send me away. They would send me home. We now have a name for this. It's called Impostor Syndrome. And it's where somebody comes into some situation which is quite demanding, like somebody from the provinces coming to a major university. And they're quite sure they should not be there. And in a bad case, those people, the students or whatever, will leave immediately. It happens in Oxford and Cambridge if we're not careful. Within the first week, the student is gone home again. Well, I had had quite a fight to get to Cambridge, so I was not going to go home of my own accord, but I did expect them to decide they had made a mistake, and I did expect them to throw me out. More discomfort. Within the first week, the new radio astronomy graduate students, me included, were given a set of tools. These are my tools. I still have them. These are not microelectronics tools. These are heavy-duty wire working tools. And for the first 2 years, I was involved in building a radio telescope. It was an enormous radio telescope, area of 57 tennis courts, and it took 6 people 2 years to build it. My responsibility was all the cables and connectors, and here I am. It's cold in England in winter, and my assistant, and I'm checking the connections here. They're all good connections. This is the finished radio telescope. The wooden posts are the most obvious thing, but they are only there to keep the wires up above the wet grass. It rains a lot in England, and wet grass is an electrical short. So all these wires have to be above the wet grass. These are the antennae running along here, wires down, cables down, and so on. There was almost 200 kilometers of wire and cable, and that was my responsibility. There's over 1,000 wooden posts, and works at 81.5 megahertz. And the receiver did not use transistors, it used vacuum tubes, or valves as we call them. The purpose was this: quasars are very compact radio sources, and a compact radio source, when we see it through the solar wind, which is not smooth, its brightness goes up and down, up and down, up and down. It scintillates. This is a time scale of 1 second. Radio galaxies, which are much broader, we see through some gaps and through some clouds, and they don't do anything like this. They're probably just something like that, much steadier. So we look for sources that change their brightness like that, which scintillate, and it's probably a quasar. There's a pattern, there's an example that's not a perfect example. On a swimming pool, these bright and dark areas, if you lie on the bottom of the swimming pool and look upwards, you see the bright and the dark go past over you. Well, it's a bit like that with a quasar. So I'm going now to 1963 and California, and a Dutchman is working, Dutchman called Martin Schmidt, is working in California. He's interested in these objects that appear to be these very bright radio sources. And he's got an optical spectrum of one of them. And he cannot make sense of the optical spectrum. It looks a bit like hydrogen, and hydrogen is very common in the universe, but it's shifted away to the red end of the spectrum. He's forced to conclude that it is hydrogen with a large redshift. The source is moving away from us at considerable speed. Now, because of the way the universe expands, the more distant objects are apparently going away from us faster. So a large redshift, a large velocity away from us implies a large distance, which means these objects must be very, very powerful to appear so bright. A colleague is working along the corridor on the spectrum of another quasar. He's busy writing a paper trying to explain why his object has a lot of tellurium in it, because tellurium was the only thing he could get to fit the spectrum. And Martin comes in and says, "Do you think your spectrum could be hydrogen with a large redshift?" And he looks at his spectrum and yes, oh, it could be hydrogen with a very redshift, even larger than Martin's. So these two optical astronomers are saying that the strong radio sources that the radio astronomers are picking up are very, very distant, something like 3 billion light years away. Martin went home that evening to his wife and said, "Something terrible happened at the office today." He was so shocked by what he had been forced to decide. Well, when I started this project, there were only about 20 quasars known. The project was to find more, and they could be picked out because of their scintillation, their twinkling. I, having spent 2 years building the radio telescope, was responsible for debugging it, getting it working, and then I used it for the first 6 months. And I found about 180 more quasars. So the number went up from 20 to 200, which was a good size of sample. And that was what my project was about. The university at that time had one computer for the whole university. It took up a whole room because it was before transistors, or before transistors were common. It was built with vacuum tubes or valves, and it had memory comparable to your laptop. So not many people could have time on it. And we did not have access to that computer. So my data came out on paper charts, rolls and rolls and rolls of paper. There was 30 meters of this every day. It took 4 days to scan the sky. And after 6 months, I had more than 5 kilometers of this paper. And I quickly got used. Oops. There we are. We got used to identifying the quasars, but just occasionally there was about 5 millimeters that showed a signal that I couldn't understand. We got lots of interference, of course, it's a big radio telescope. We got quite a lot of quasars, but this didn't make sense. I didn't understand it. And the first few times I saw it, I marked it with a question mark and passed on, because there are meters and meters and meters of this chart paper to be scanned. And then my brain one day said, "You've seen something like this before, haven't you? You've seen it from this bit of sky before, haven't you?" And then it's easy, because I have the charts stored in shoeboxes by declination, by the strip, the latitude on the sky. So I get out the shoebox that covers this patch of sky, lay out all the previous observations, and no, oh, it might have been there. Oh, it was there. I logged it with a question mark. And it's not there, and it's not on that one, and it's not on that one, but it might be on this one. So 3 times previously, I had seen something like this from this bit of sky. Often it's not there, but when it is there, it's from the same bit of sky. It occupies about 10 parts in a million of the chart paper. So it was a bit of a miracle that I noticed it and remembered it. But of course, I thought they were going to throw me out. So I was being very, very careful and very, very thorough. And that's how it was noticed. Ultimately, I got a higher speed recording where the paper went faster under the pen and everything gets spread out. Here are 1 second time marks. And here's the signal that came in: blip, 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 blip. It's got a period of about 1 1/3 seconds. And because the pulse sides are steep, it's small. We'd never seen anything like that, nor had anybody else. My supervisor thought I was crazy. He came out the next day, stood looking over my shoulder, saw it for himself. The pulse period was still the same, 1 1/3 seconds. So it's not getting tired and dying. It's keeping going. Bump, 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 bump. What is it? Well, first thought, it's radio interference, but it keeps the sidereal day, 23 hours, 56 minutes. Next thought, Jocelyn has wired the radio telescope up wrongly. But we got a colleague with another separate radio telescope and receiver, and they picked it up too. But it's a big problem. It's got to be small because of the short, steep pulses, and it's got to be big because it's keeping accurate time. I'm looking for it every day, and it's still going at the same rate. Then a colleague managed to get a dispersion measurement, which gives an estimate of distance. and showed it was about 200 light years away. So it's beyond the solar system, but it's within our galaxy, the Milky Way. My thesis advisor wondered if it was little green men, aliens, signaling to us. Now, if they are aliens, they probably live on a planet that goes round their sun. So some of the time they're coming towards us, and some of the time they're coming away from us, towards us and away from us, towards us and away from us. And as they come towards us, the pulse period would be shorter. And as they go away from us, the pulse period would be longer. So we looked for that. We succeeded in proving that the Earth went around the sun, because motion of the observer can also give a Doppler effect, but we saw no motion of that source. And then, thank goodness, I found a second, a third, and a fourth. So this has to be some kind of new object, and there's lots of them, and I've just found the first four. It caused great interest. We were interviewed by many newspapers. The science correspondent of one of the big newspapers, Anthony Michaelis, came to us and said, "What are you going to call these things?" And we had given some thought to this. We said, we're going to call them pulsating radio sources. The other option was pulsed radio sources, but pulsed radio sources suggests there's somebody or something making the pulses. So it was pulsating radio sources. So we said to him, pulsating radio sources. He said, no, a short name. What about pulsar? Because we already had quasars. So pulsars they've become, an abbreviation of pulsating radio star. So we now know of several thousand of these. What are they? They are very small stars. They're spinning. They've got strong magnetic fields, maybe best seen in the right-hand diagram. Spin axis vertical, magnetic field inclined, and somehow out from the magnetic poles, there comes a beam of radiation, radio waves. And if the beam shines in our face, like now, we see a pulse, and now, but we don't see the beam from the other pole because it misses the Earth. So this is the picture we have of pulsars today. These are what we call neutron stars, very small, 10 kilometers radius probably, but the same mass as the sun or even a bit bigger. So pulsars are small, they're very dense. We believe they're rich in neutrons, so we call them neutron stars. They've got very strong gravitational fields, very strong electric and magnetic fields, and they're rapidly spinning. Massive stars end their lives with an explosion. It's called a supernova. And we believe that these stars were once massive stars. And when they exploded at the end of their life, they leave a core when they explode, they leave a core at the center of the star, and the rest of the material goes out into space as a supernova. So we think these neutron stars are the remnants of stars that have exploded, the remnants of supernova. I'm not sure if this audio will work. Let's see. No, the link's not going to work. Sorry about that. They're primarily radio emitting objects, a few in the visible, some in the X-rays, quite a lot in the gamma rays, which is a little bit surprising. Of the 3,000 known, 30,000, there's a typo there, 3,000. There's about 20 that are visible, about 100 that are seen in X-rays, and 200 in the gamma rays. About 10% are in binaries, twinned with another star. One is a pulsar-pulsar binary, There's one triple system, and there's a few with planets. And there might be 100,000 in the galaxy. And we believe they come about when a massive star reaches the end of its life and explodes in what we call a supernova. And these two photographs are about a supernova that we observed in 1987. One star here is picked out. Please note the arrow was added after the photograph was taken. There are not arrows in the sky telling us where to look. But look at that corner of the photograph. That tiny little star has exploded. And we believe that at its core, it formed one of these pulsars, well, neutron stars at least. Crab Nebula, Messier 1, is a famous object in the night sky. It's the remains of a star that exploded in 1054 AD. And it was always a bit of a puzzle why it was still shining so brightly. We now know there is a pulsar about there. And it's the pulsar that keeps the brightness, keeps it shining, prevents it from fading. If I may, I'll tell you a few stories about how pulsars were nearly discovered, because there have been some near misses. The first one is in summer 1957. We are in Texas at the McDonald Observatory, and the Struve telescope is looking at that center of the Crab Nebula that I just showed you. Elliot Moore was working there as a summer intern. And members of the public step up to the telescope and say, "Oh, wonderful, gee," etc., all the things people say. And a young woman stepped up to the telescope and said, "That star's flashing." And the night assistant started to explain about turbulence in the Earth's atmosphere and how the brightness of stars can change. And she said, "No, that star's flashing." She went on, "I hold an airplane pilot's license." This is 1957. "I hold an airplane pilot's license. My job is to fly aircraft from the construction factory to the customer. I fly at night. There's not a lot to do in the cockpit at night. I know about the scintillation of stars. That one's flashing." We now know she was right. It flashes very fast, about 30 times per second, 30 hertz. But some people can see flashing at that rate. In Canada, the electricity power supply used to be at 30 hertz. And some people, particularly young women, could see the flashing. And it drove them crazy, as you could imagine. Nobody followed up on what she was saying, but it turned out that the Crab pulsar is flashing at 30 times a second, 30 hertz, and we know some young women can see that rate of flashing. So we think she saw it, but nobody followed up. Otherwise, pulsars would have been discovered in 1957. And here's another story about the same pulsar. Much more recent, Australian radio astronomers get an email from an American man called Charles Schisler. He said, this is him here in the distance, sitting next door to me. As a United States Air Force technician during a one-year period back in 1967-68 at a ballistic missile early warning site in Alaska, I discovered 14 pulsing signals on our extremely powerful radars. What was happening was that when things were quiet in Alaska, when there was no Russian missiles coming in, he was allowed to play with the equipment. And he used it in receiving mode, and he found several pulsing sources up in the sky, which were not ballistic missiles coming into the United States. He had done an astronomy course at college, and he made a note of the approximate right ascension and declination of these pulsing sources, and probably illegally took that piece of paper away with him when he finished serving as an Air Force technician. He's just discovered the online pulsar catalogue that the Australian astronomers host, and several of his objects are in it. He probably was observing pulsars, one of them being the crab. Another story, also from the crab pulsar, but about 10 years later, 1967. Sue Simpkin. Sue Simpkin was born in Canada. Sue Simpkin suffered from the 30 hertz Canada power supply. She said as a child she was driven crazy because all the lights and the television and everything was flickering at 30 hertz. She can see 30 hertz. She's going to take an ultraviolet spectrum, and Dutchman, Low Vulture, asked her to take a spectrum of that funny star in the middle of the Crab Nebula. Sue did it, so she said the spectrum was dull, but as she observed it, she saw flickering, or as if there were waves going out from it. Low didn't believe her, but when the crab pulsar was discovered, he was man enough to say she must have seen it. But that one didn't go any further either. This example, I'm not going to name the people involved. The lead scientist was the person involved. He was always very embarrassed about this. And although he's no longer with us, he probably would not have liked me to name him. But some astronomers are making a 408 megahertz survey of the sky, European astronomers. And they're using big telescopes when and where they can get time on the big telescopes. So they're observing with things like Jodrell Bank. And in fact, this observation happened, I think, with the Jodrell Bank telescope. So they've done rather well mapping the sky, but there are a few little patches that they still have to survey. And they're surveying these little patches. They're using pen recorders because it's pre-computers. And one of the pen recorders tends to stick. It's not working very well. About 2 o'clock in the morning, one morning, that pen recorder started misbehaving. It went jerk, 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 jerk. And the observer thought, it's that pen recorder again. And he did what you always did with equipment that was misbehaving. You thumped it. And it stopped doing jerk, 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 and went back to normal. And he said, good, put on his coat and went home to bed. He did not make any note in the logbook. He had actually been observing a pulsar. We now know that at that point in the sky, there is a pulsar. Even following the discovery of the first 4 pulsars, which did not include this one, they didn't think to go back through their data looking for pulsars. Another near miss. Finally, just a few factors that I think led to discovery when and where it happened. I had my own telescope and my own receiver, and I made sure I understood how they worked. I was a graduate student, a research student, so I've got time and space to follow up anomalies. And because of that imposter syndrome, I'm being really, really thorough. Anomalies are followed up. This is one of the first surveys with a short time constant, or a new area of phase space, as they say. It wasn't a good frequency for finding pulsars, and the first ones were not the strongest. But if you're going to make a crazy discovery, it's good to have a good address. And Cambridge University has a good reputation. It's become fashionable for funding bodies to ask people to specify what are their objectives when they apply for money. And then afterwards, they get a grade depending on how well they've met their objectives. this wasn't one of our objectives. Would we have been marked down for deviating from our objectives? Alternatively, if we had computerized the search, would pulsars have been discovered? Franco Pacini was a very able Italian scientist. A few months before the discovery of pulsars, Pacini published a paper in Nature, the leading magazine. He too was puzzled by why the Crab Nebula kept shining, and he suggested that it was energized by a neutron star with a large magnetic field inclined to the spin axis, and that there would be energy dumped from this system which couldn't escape the plasma. And he was absolutely right. A pulsar in the Crab Nebula is a neutron star with a large magnetic field inclined to the spin axis, and the radiation gets dumped in the nebula, so it keeps shining. He was an amazing scientist. And I finish with a photo of the group we have in Oxford, people doing pulsar work. Thank you for your interest and your attention.
Okay, thank you very much for that very interesting talk, Professor Jocelyn Bell-Burnell. That was very, very interesting. As a person from Britain, a person from Wales, I liked your map of Britain, and it was very interesting hearing about the different, nearly attempts for pulsars, which aren't recorded so much in the history. So that was a fascinating part of the history of astronomy and the near misses. First, I'd like to ask you about the Breakthrough Prize that you won in 2018, for which you've used all the money to set up fellowships and scholarships for young students. So would you like to talk about a bit about this fellowship scheme?
Yes. The Breakthrough Prize was $3 million, which is an enormous sum of money. And I did not feel I needed it for myself. And so I approached the Institute of Physics in Britain to see if they would use it for research studentships for students from different backgrounds. I thought one of the essential ingredients in the discovery of pulsars was that I was not from the south of England. I was feeling out of place. I was feeling impostor syndrome. I was working very, very hard as a consequence. And I also know that diversity is very important in every area of life. So I suggested to the Institute of Physics that they might set up studentships for people to do PhDs in physics, but the people were not to be white men, because we have lots of white men doing PhDs in physics. And we don't have many women, we don't have many people of color, we don't have many refugees, we don't have many minorities of any sort. And so I wanted to promote some of these minorities.
Yes, that seems an excellent scheme. I think those of us from Wales sometimes have experienced imposter syndrome as well, so I could relate to that too. I don't know how much you know about our book fair, but usually this event is in quite a big room and the audience is quite knowledgeable. Amateur astronomers, people from astronomy societies, the physics students and other science students. What advice would you give to a young physics student these days?
If you like physics, if you can do the physics, I would say go for it. There are a lot of interesting frontiers being addressed in physics these days. A large portion of the universe, what we call dark matter, is stuff we don't know what it is. So there's work going on to try and discover what dark matter is. There's lots of fundamental research going on, particularly, for instance, in connection with gravitational waves. People will know about the electromagnetic spectrum, but we are now discovering a whole other spectrum of what are called gravitational waves. Can I give a quick explanation of that?
Yes, of course. Go on.
Okay, so here is my mug. If there's gravity between me, my mug, my laptop, if I move my mug the pattern of gravity changes. And that change in the pattern of gravity has already gone off out into space at the speed of light. It's a very small change. But imagine this was a black hole, and imagine it's going round something. Then the pattern of gravity is changing quite strongly and regularly, and a whole wave in the gravitational field is going out into space. And just recently, we started being able to pick up these patterns in the gravitational field, these waves. It's called gravitational radiation. And there's quite a lot of physics still to be done in that, as well as the astrophysics. So there's a lot happening, lots of interesting things, lots of excitement, lots of new things.
Yes, I think they also involves pulsars, doesn't it? Some of the gravitational waves detections are pulsars, black holes, and pulsar and black hole fusing.
Yes, the strongest sources are where you've got two black holes, but if you've got a black hole and a pulsar, it's still quite a strong gravitational wave signal. And they've even found a few cases of two neutron stars. So, yeah.
Yes, I think the detection of gravitational waves must give some hope to those who are in the dark matter detectors as well, that one day they'll get a discovery.
Yes, yeah.
I also said in the introduction, mentioning your productive summer of winning various medals for the Royal Astronomical Society Gold Medal, which I watched that ceremony. All the winners seem to be from Northern Ireland in one part, and the Copley Medal of the Royal Society, which you were only the second woman ever to win that medal. Would you like to talk a little bit about that?
Yes, the Copley Medal is the top award given by the Royal Society in Britain. It was first awarded in 1731. And if you look at the names of the recipients, it's all the big names in physics, all the people, you know, who have laws and things named after them, as well as non-physicists. I mean, there are some chemists and some biologists and some mathematicians as well. So it's not just physicists. There's been one other woman won it around about 1956, I think. She was also from Oxford, which is rather nice, but she was a chemist, not a physicist.
Yeah. Interesting. And you've had quite a varied, interesting career working in various universities, institutions. We saw James Clerk Maxwell Telescope, Open University too, which is a sort of, I think now feels like a pioneer for those of us in lockdown in the last 18 months. For doing only remote teaching. The Open University in Britain was one of the first institutions to give it remote education for people who were working in the day, so they could attend university. Would you like to tell us a bit about the Open University and your varied career?
It was also good for people who were very remote. So I taught with them for a number of years. One of my students was a lighthouse keeper on a lonely rock way offshore. And another one lived in a very remote part of the Shetland Islands. And people who worked on oil rigs in the North Sea. Because it's distance learning, all these people can take part. It was fantastic. And there were some brilliant students amongst them who for some reason had missed out on university education at the normal age. So they were real fun to teach. But it's also quite challenging teaching remotely, as you know. I think my biggest challenge was we were talking about the right-hand rule and the left-hand rule. And one of my students says to me on the telephone, no visual link, "Can you tell me, am I using my right hand or my left hand?" No, I can't tell you. But I found a way of setting up a right-handed system that I could describe over the phone, involving 3 pencils. Real fun to teach it.
I was just thinking that could be complicated now as well, because even with video, because sometimes the screen is reversed, and so you might get confused about the hand.
Yeah.
How would you sum up your career now after all these varied experiences, and what plans do you have for the future?
I think it's been a very miscellaneous career. partly because I was a married woman for quite a bit of it. And my husband had to move job every few years. So I moved job every few years. So I went from radio astronomy to gamma ray astronomy, from gamma to X, from X to, where did I go next? Infrared and millimeter. So I've covered most of the spectrum, always doing some kind of astronomy, which was really, really interesting. And quite often very new cutting edge stuff with new telescopes. So it's been huge fun. I've been really, in many ways, very, very lucky.
Yes, a fascinating career and a fascinating part of the history of astronomy you told us today. Jocelyn, I said we did invite you to this a couple of years ago, presential form, but you couldn't make it that time. We're glad that you made it this time, and we hope you can maybe come again in future years if the world gets a bit more stable and calm. But you have visited Mexico before, I know, and
yes,
in giving a series of talks with Dr. Omar Lopez Cruz. Would you like to tell us a bit about your experiences in Mexico?
Yes, that was an opportunity to visit Mexico City. And it was also my first ever visit to Mexico. So it was hugely interesting and hugely exciting. And met a lot of students and faculty who were real fun to meet with and talk to, and did several lectures and really just had a lot of fun, and got taken, I've forgotten the name of the site, but got taken to a very ancient site not far from Mexico City where there were some pyramids. So all very, very interesting.
Could be Teotihuacan. That's a very big city near, about
yes.
half an hour outside Mexico City. Or
that
so.
Sounds right. Thank you, Simon. Yes.
Very large. Okay, how are we doing? Okay, but I think we've had about 10 minutes of questions now. So again, thank you very much, Professor Jocelyn Bell-Burnell, for your contribution to the Guadalajara International Book Fair. I will send you some photographs of that, or send to your PA some photographs of past events so you can see a bit what it was like. We've had a few of these colloquios now, and now I'll give.
Thank you very much for the opportunity to be part of it.
Again, thank you too for your excellent contribution. And I'll now give the closing message in Spanish, because this is the last talk of this colloquium. Bueno, gracias de nuevo a la doctora Jocelyn Bell-Burnell para su excelente contribución a su plática muy interesante. Este es el último evento en el coloquio de astronomía por este año. Gracias a todos que han seguido el evento durante el día, y espero verlos de nuevo en coloquios futuros. Muchas gracias a todos.